Hello everyone, this is Nitish Patil. Today I am going to discuss about curse of dimensionality. So let me share the screen. Yeah. So what can we understand about dimensions? So dimension means features. So whenever we are talking about any kind of features in the data set, so this is called as the features which are going to affect the data set. So basically, we will have some features which impacts the data set. And this is also called as dimensions. So now, whenever we are applying model into our data set, so that time, let's suppose uh, we are preparing a model that is M1, then M2, M3, M4, M5, M6, M7. So these different type of models we have, and we are taking an example like house price prediction. House price prediction. So in this example, if we will have five features only, and in some other case, we will have 10 features, and in other case, we will have 20 features, then 30 features, then 100 features, then 1000 features, and 10,000 features. So how it is going to impact our accuracy? So that we'll see here, the accuracy. Yeah. So here, whenever we are going to talk about, if we will have a five features, then it will have some accuracy. And if we are going to increase this as a 10 features, then it will have uh, some other accuracy. Then we'll have 20 features, then it will have some other accuracy. Then 30 features, it will have some other accuracy. So if we are increasing the features, so how it will going to impact this? Like if we five feature means it it will not be going to give us the proper result. Like maybe some 70% or 60% accuracy will get. Then if we are increasing this up to 10 features, certainly it will may increase till 80%. Then 20 features, like that if we are taking this as a threshold, 30 features, 100 features, 1000 feature and 10,000 feature. So it will, the 10,000 features is not feasible because, and 1000 feature also will not be feasible, 100 features also not be feasible. Up to 20, we can get a good amount of uh, result for the accuracy. So this is called curse of dimensionality. Unnecessarily, we cannot increase the features. For example, if we are taking house price prediction means the number of bedrooms, the house uh, addresses, and number of washroom. These features can impact the uh, accuracy. But if we are taking the movie hall, how much it is near from the house, a particular house, and some other feature also, which are unnecessarily we are creating here, and we are going to give the extra burden to the data set. So this will not impact our particular, let's say, the models. So it will not give us the feasible solution. So if we are taking till from 5 to 10, 5 to 20, or let's suppose 30 also, then can give us the good features, right? So this is called the curse of dimensionality. Now let's suppose another example. If I'm taking another example, for example, if we have some images of digits, the MNIST dataset, if we have the MNIST dataset where we have multiple digits are there. So there, if it is written 7 or 1 or 2. So in that case, what happens? The range of this area can give us the good prediction about the digit. What is this digit? If we are expanding like this, if we are expanding the area for getting the better uh, prediction, so it will not be feasible in that case. Just we are increasing the dimensions, but it is not in use for us. This is not useful. Only this area we will cover up, then only we can get the feasible solution. So how it is going to calculate the this area, like 28 by 28 pixels, 784 pixels area is there. So in that, if we are trying to find out the digit accuracy, which digit it is, whether it is 1 or 2 or 3 or 4. So based on this, we can get the value up to this area. But if we are expanding this, this is of no use. So this is unnecessary. We are increasing the dimensions. So this example is also called as curse of dimensionality. So how it is going to do, like, it is a higher dimension space, and like if we have some images, and if we have some text data, let's say text data, if we have in those application areas, we can lead to curse of dimensionality. So these two things we can get up, and we'll get the dimensions problem, and it can lead us to not getting a good feasible solution. So that should be removed. And what it does for algorithms, it decreases the performance. What it does, it decreases the performance, and the computation time can be very high. So that also one problem we'll face. But it should not be like this. Uh, this should be very feasible. And let's suppose, for example, if we have KNN algorithm, KNN, KNN algorithm. So in that, what we are trying to solve, we are finding the nearest neighbors. So like this, like this, like this. Yeah. So like this, we are trying to find out which one is the nearest neighbor. So if it will be up to the nearest, to the centroid, then we can be able to find out using Euclidean distance or Manhattan distance. But if we are getting it much far, like this, if we are putting the data points. So it is not feasible. Like, how can we say that it is a nearest neighbor to this particular centroid? So this is also a big problem here, and we cannot spread the data much over here, and the dimensions we cannot increase over here. So this is also another aspect where we can face this curse of dimensionality. And let's suppose one layman example, if we say, if we can take, like, we are trying to find somehow one place which is in the road. If we are going by road and we are trying to find out that place that we forgot where it is, then maybe it will be easy. But if we are considering a large area and we are trying to find out this place, so it will be difficult for us to find out, because again it is expanding the area. So it should be always be optimal, and we must know how much uh, like features is required to get this particular solution. And if we are taking in 3D spaces, so that also again it will be difficult. So this is 2D space and this is 3D space. Here, if we are trying to find out that particular area, then it will again be a problem. So we are just expanding our complexity and we are expanding our dimensions where we are trying to find out this. So this will create a problem and will not be able to find out this all. And this is also called as sparsity. Sparsity of the problem. Sparsity. Sparsity means that it is very far from the particular place and we are not able to find out this. So this is called sparsity. So it leads to the sparsity problem also when we are dealing with more and more dimensions. So this should not be there. And this is called the curse of dimensionality. How can we overcome this? So we can reduce the number of columns. We can reduce number of columns, and it has some algorithms which will solve this curse of dimensionality problem after reducing the dimensions. So these algorithms are PCA, then LDA, and then TSNE. So these kind of algorithms are useful to solve the problem. Or let's suppose if we say we have F1, F2 up to Fn features. So from this, we can take some feasible features, F1, F10, then F18, then F20, like this. So if we are taking like this from the bunch of features, the useful features, then we can be able to solve the problem properly, and it will give us the proper accurate solution. So this is all about the curse of dimensionality. So what we have seen today, how can we find out the dimensions the optimized dimensions, which can give us the proper result and the good accuracy. So finding about the dimensions and the proper dimensions which will useful for the data set, and then we can get the accuracy for that, but after applying the algorithm, then we'll be able to solve the uh, problem appropriately. So this is the basic idea about working with this the curse of dimensionality problem, and we have the solution also. After applying these all algorithms, we can be able to solve the problem. So that's all about this topic. Thank you so much for listening me. Thank you.